Welcome you all to a new session. This is the continuation of our registers part 2. Here we are going to continue from the topic called parallel in parallel out shift register. Now here the parallel in parallel out means you know that the parallel in or parallel out takes only one clock pulse. So for one clock's edge I am going to store my data onto my 4 flip-flops, and the next clock pulse is going to give my 4 bit of information as output here. Similarly to that of my previous topics, here it is going to have 4 flip-flops here, 1, 2, 3, 4, and each flip-flop is attached with one clock pulse here, and 4 inputs are provided here. You see the data is given as 1101. Now this requires only one clock cycle. When I am having a clock 1 applied, 1101 gets stored onto these particular 4 flip-flops. Or next, what happens on the next application of my second clock pulse, what happens, this particular data is going to appear as output. So the data at QA will be 1, QB will be 1, so QC will be 0 and QD will be 1. So it requires only 2 clock pulses to store the data and to read the data from the register. So this is what about the parallel in parallel out shift register. Now coming to the next thing is universal shift register. We have seen serial in serial out register, we have seen serial in parallel out, next parallel in parallel out, and parallel in serial out registers. The last final thing is the USR, that is universal shift register. Universal shift register means it is going to perform right shift operation, left shift operation, and parallel load operation. Means in one setup we are going to see these 3 kinds of operations in it. Now to have these kind of operations on my flip-flops, we are going to take one multiplexer. So why? Because you know the operation of multiplexer, that it is going to have multiple number of inputs, but it is going to provide only one output out of those multiple number of inputs. So I am having here 4 operations. Those 4 operations means I need to have 4 input lines for a mux. So these 4 operations are provided as inputs for my 4x1 mux for everything. Now each flip-flop will have one mux here. Each flip-flop is going to have one mux, and this mux inputs are provided with serial input from the left shift for left shift, serial input for my right shift. Means I can perform either right shift or left shift using this particular setup. Second one is I need to load the data parallelly in. You can see here I3, I2, I1, I0 are attached as third connections for each flip-flop. Third connection in my mux, that is 4x1. So first line in my 4x1 mux is the parallel load operation. Now once after parallel load operation, what happens? To shift right operation, I am providing 1 bit as a 1 input as my right shift operation. Now if you observe, for left shift operation, second line is provided as input for my all 4x1 mux. Next, for having no change, means the register should be at a constant position. For that constant position I am providing these zeros. So 4 input values are provided with 4 operations here. Now out of these 4 operations I need to choose only one operation, that is based upon my selection lines. So for 0, 0 operation there will be no change in the data. For 0, 1 operation I am going to perform right shift operation. For 1, 0 operation I am going to perform shift left operation. For 1, 1 I am going to perform parallel load operation. So this is what we are going to perform for each set of selection lines. One particular operation is going to get performed here. Now for all these things to be happening, now these outputs, you observe the outputs which are coming out of my mux are getting directly connected to my 4 flip-flops. This is my first, second, third and fourth flip-flop. Directly the output operation which has been kept as an input for my 4 flip-flops, and my 4 flip-flops are provided with one clock and clear. Clear means the signal which is used to clear all the 4 values which are present on my shift register. Clock means to trigger my flip-flops to store the data or to shift the data towards right side or towards left side. Now once the data is stored, the outputs are collected from A3, A2, A1 and A0 terminals, and these all 3 terminals you can see, observe clearly that these are outputs connected to these lines, and these lines are used for parallel out operation also. Means I can do parallel load and parallel out, serial left, serial right. So everything operation is everything is covered under one single setup. That's the reason we are calling this as universal shift register. Okay, this is what regarding the universal shift register. We'll get into the next thing. Now the topic is related to the counters. Now the counters means like it is similar to that of our registers. Like here we are going to do some counting based upon the step size. So the counter is a register capable of counting the number of clock pulses arriving at its clock input. As I told you that counter is a type of a register which is going to do counting operation. Now the counting can be either ascending order or descending order. Ascending order means it is going to do up counting, and a descending order means we are going to do down counting for that particular. That is what the counting is of two types, up counting as well as down counting. Now up counting will be performed for all the positive edge clock pulses of a signal, whereas down counting will be performed for negative edge clock pulses. And counters are of two types, synchronous counters and asynchronous counters. Synchronous counters means the counter when it is working along with the clock pulse, then we are going to call that as a synchronous counter. Means why? Because it is in sync with the data which is we are providing as an input to the counter. Whereas asynchronous counters means all the flip-flops which are present under that one particular setup of counter will be having a different clock pulses along with the data input. That's the reason it is called as asynchronous. In sync with the clock, which is not in sync with the clock. That is the difference between synchronous counters and asynchronous counters. Positive edge clock pulse, up counting, negative edge clock pulse, down counting. Okay, we'll get onto the topics. Now this is state diagram for mod 10 counter. Mod 10 counter means we are going to have 10 states here. State mean now mod 10 counter will have setup like this. This is my state 0. This is my state 0, state 1, state 2, state 3, state 4, state 5, state 6, state 7, state 8, state 9, state 10. So mod counter, mod 10 means it is with the help of name itself we need to justify that it is going to have 10 states. In exam we are going to have these kind of questions as a short questions. Now mod 10 itself it is representing that it is going to have 10 states, and the 10 states movement we need to write in that particular state diagram. That state diagram should be represented using a binary values. Now you know state 10 means it should begin with 0 and it should end with 10. Now 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So now after once reaching by its maximum value, it should reset back to its initial position. When it has reached to the 10 value, it should get onto my initial value. So that is what the reason the connection is getting onto my initial position. So this is what the diagram which is representing about a mod 10 counter means it is getting counted from initial state to final state. Now this is up counter. Now up counting means you know the counting should go on an increasing order. Now on increasing order we are having a 2-bit up counter means I am going to perform up counting on 2 bits means the counting should start with 0, 0 0, 0 1 as 1, 1 0 as 2, 1 1 as 3. So it is going to have completely 4 states. 4 state of information it is going to have represented with this kind of setup here. Now I am using a JK flip-flop as a setup. As you know that each bit will be stored under one flip-flop. So I am having 2 bits, so 2 flip-flops are required here. So for 0 0 for the first initial state 0 0 should get stored onto my first clock pulse. Now whenever I am applying this clock pulse, this is my clock, this is also my clock. The only one thing which we need to remember in under a 2-bit up counting is that the output of my first flip-flop should be connected as input for the clock of second flip-flop. Why? Because the output of first flip-flop is coming from positive end. This is my negative end. Whenever I am doing down counting, then negative edge has to be connected as clock for the next flip-flop. So this first flip-flop I am connecting as our clock input for my second flip-flop. Now if you observe, if I am providing a high signal means logic 1 I am providing as input here. Now whenever I am providing logic 1 as an input here, this along with my edge triggering, a 0 comes and places under first flip-flop. Now this should be moved on to my second flip-flop. Now how this positive edge is getting connected to the clock input of my second flip-flop. So that's the reason if we observe Q0, this is my Q0, this is my Q1. So Q0 and Q1, if you observe, the first initial values are 0 and 0. Now when high signal is passed, what happens? The first flip-flop is going to receive first 1 value. But whereas my second flip-flop will have still only remain with 0. Now what happens for the next signal? This 1 will move on to my second flip-flop. So this is what the movement of direction. That is, the data from first flip-flop is moving on to my second flip-flop, and this remains on my initial state. Again a high signal is applied at my first flip-flop. What happens? This signal will be converted to 1, but still my second flip-flop is stored with 1 value only. Why? Because this requires a change of value with 2 clock pulses. Whereas change of value for my first flip-flop will require only 1 clock pulse. The data is stable here for 1 clock pulse, the data is stable here for 2 clock pulses. So that's the reason if we observe the output of second flip-flop is constant for 2 clock pulses here. Now when you observe the order of this particular thing, Q1 and Q0, so this will be 0 0, this will be 0 and 1, this will be 1 0, this will be 1 1. Now this is in decimal it is 0, in decimal it is 1, in decimal it is 2, in decimal it is 3. Now if you observe clearly, the counting is going in a up trend. So that's the reason we call it as 2-bit up counter. Let's see the same thing with our down counting also. Now this is your down counter. As I told you that this particular thing, the output of my first flip-flop should be connected through a negative edge here. Now through negative edge if I am connecting, this negative edge will move as a clock input for my second flip. Now here, when negative edge is connected, this 0 becomes 1 here at the first instance itself. Now when it is becoming 1, the first input will come as Q0 and Q1. The first input will come as 1. Here the output is also taken through Q bar. So that's the reason I am taking 1 and 1. So next thing what happens, this becomes 1 and this becomes 0 for the next instance of time. For the third clock pulse, for the third clock pulse, what happens, this becomes 0 and this becomes 1. And for the last instance, this will be 0 and 0. So the counting will be 1 1, 1 0, 0 1 and 0 0. So this in the decimal it is represented as 3, this is represented as 2, this is represented as 1, this as 0. Now if you observe, the counting is going from up value to the down value. So that's the reason we are calling it as a down counter. Only one difference, in the previous case the output of first flip-flop should be taken from positive edge, whereas for down counting the output of first flip-flop should be collected from negative terminal, and which is provided as input for my second flip-flop. So this is what related to up counting and down counting. We'll see in the next session related to up counting and down counting in one block diagram. Thank you all.